Hello. So, good evening, everyone. Welcome to the week 11 live session of the NPTEL course Design of Reinforced Concrete Structure. I am Sanjay Kumawat, and today we will be discussing some few questions on design of footings. So, in the last few classes, or in all of the classes, what we are discussing till now is the various components of a structure, and those components were specifically, if we talk about, they were beams, columns, slabs, and now today we will be looking at the footings. So, in beams, also, we have seen different types of design, such as singly reinforced and doubly reinforced. In columns, also, we have seen different types of columns. In slabs, also, we have seen different types of slabs, one way, two way. But in footings, in this course at least, we will be only looking at design of only one kind of footing, which will be the shallow footing. So I would not be going much into the classification of the various type of footings, because all of those things you already must be familiar with from the course content, and we will be mostly focusing on the problems. So to begin with, firstly, let's talk about the load distribution in footing. So what does footings generally do? So basically, when we talk about the overall structure, the structures has various components such as beams, slabs, columns, and footings. So from the beams, the load is transferred to the slabs. So if I draw a schematic, then roughly it would be like this. So if these are the beams, then the on the beams, the slabs are transferring the loads. So slab will transfer the load to the beams, and the beams will transfer it to the columns, and the columns will transfer it to footings. So in this manner, the load transfer takes place. So when the what role footing has to play is, it has to transfer the load of the superstructure to the soil. So what important loads which come up for the footing is the gross soil pressure. So this pressure is nothing but the reaction. The actually, what pressure is given by the superstructure, the similar reaction, it is transferred by the soil to the footing. So basically, we need to design this footing for this gross soil pressure. And this gross soil pressure, when we assume this gross soil pressure to be of constant constantly distributed UDL, then the gross soil pressure, we can just simply uh, like formulate it as P plus delta P by A. Why? Because P is the pressure which is coming onto the column, as you can see it here. So this uh, pressure which is coming onto the column is due to the superstructure. Now we are adding this pressure with some additional load, delta P. This delta P, it will be considering the surcharge load. What is surcharge load? You must have studied in the geotechnical subjects. Surcharge load is nothing but the load due to the soil. This is the soil, as you can see it here. So there is some load because of soil on the footing. So this delta P, it is an additional load due to the surcharge, as well as due to the self weight of the column. Sorry, yeah, due to the self weight of the footing itself. So this is the self weight. So as long as we consider the gross soil pressure to be of constant, that is to be of uniform, or what better term should I use, if I assume is to assume this footing to be loaded concentrically, that is there is no eccentricity, then the soil pressure which will be coming on the footing would be what? It would be uniform, as you can see it here, and it can be easily calculated by a simple formula which is given by P by A. So this P by A, for this pressure we need to design the footing. Now when we come up to the second case, so this was the first case. In the first case, I talked about concentrically loaded footing, and in the second case, what we will be seeing a case of a footing in which not only concentric load, but some eccentric load would be also acting. So from where does this eccentric load would come onto this footing? Do you have any example? If you have, you can just unmute yourself and tell me. Why does this foot? Yes, yes. Actually, you are not audible. You can type in the chat
Colony
box.
being
You are not audible. I think there is some issue with your microphone, and this is not this time. This is in all the lectures, I think. Can you write it in the chat box? Because you are the only one present right now in this class. Okay, you are asking me to continue. Fine. So, what was I saying? Pressure I can understand. Pressure is due to the cell. It is the load because of the superstructure. But when we talk about the moment, this moment it is mainly caused because of some eccentric load, and that eccentric load it can be due to wind load or due to earthquake load, or it can be maybe some in the foundations are also provided for some retaining walls. So if this is the retaining wall, then there can be some soil pressure behind this, and because of this soil pressure we can have a moment on this footing. So some examples of eccentric load will be earthquake load. If there is some earthquake, then a side load would come, and this lateral load would cause some moment on this footing. So now this footing we are intent to designing this footing has to be designed for both concentric as well as eccentric load, and this eccentric load would we would consider this it in the form of moment. So now what would be the gross pressure? So because of this moment, now there would be an differential gross pressure on the soil. So this differential gross pressure, as you can see it here, so on one of the sides because of this moment the pressure will be high, while on the other side it would be low. So now this pressure we know that this column sorry this footing, since it is subjected to both concentric as well as eccentric loading, due to concentric pressure it will have a gross pressure of P by A, but due to moment what will be the pressure? M by Z. Can any one of you tell me how does we get this M by Z? What is this M by Z? So pressure due to concentric load, it is directly force by area. But when we talk about what would be the stresses because of bending moment, so because of bending moment, what stress we have? We have a stress of my by I. So this can be plus minus. So y, if I bring it down, I can replace this I by I with Z. So now based upon what is the nature of moment, if the moment is negative, then I will have this case, which is the P by A minus M by Z, and if the moment is positive, then I will have this other case. So I hope you are able to understand. So now just a basic question for you. So if you wish to answer you can answer, or if you don't wish to answer you can directly tell me, don't ask us the questions. So what is this Z? Z is section modulus. So section modulus of what? This is the footing. So this is a very simple case. I can just make you all visualize. So if this is the column, this is the footing, and we want to design this footing. This is the footing. So this is what? This is the side view. If we look at the cross section, this is the cross section of this footing. I can name this as L. I can name this as B. So what is this A? A is what? L into B. What is Z? I by Y section modulus. And when you solve this, what you will get? You will get BL square by 6. So this was about the eccentric and concentrically loaded footing. Now this was all about what type of loading does our footing can have. It can have concentric as well as eccentric loading, and based upon this loading, now we have to design this footing. So the design of footing, it has many terminologies, and these terminologies are coming both from, we have to see this footing both from structural point of view as well as from the soil point of view. So why I am talking about soil as well as structure, that I will be like explaining you in further few slides. So let's first see what are the various design considerations for the footing. So the first design consideration is the design of foundation consists of two phases, which is soil design and structural design. So now you cannot say, okay, I'm structural engineer, I don't know what is soil. That is what geotechnical engineers should be bothered. Why I should see why I should be bothering about the soil. No, it should not be like that. If you are talking about the safety of structure, that should be safety of both structure as well as soil. If the soil is failing, that is indirectly the failure of structure. If the structure is failing, soil is not failing, that is also indirectly the failure of your entire structure. So soil, you should firstly able to evaluate, or even if you are not able to evaluate, you should be knowing what is the ultimate bearing capacity of that soil, what load it can take, what load it can bear. So based upon that bearing capacity of soil, you would be building a structure on that. So design of foundation, since it is at the interface level of soil and the structure, you need to be taking care of both soil as well as structure. So let's move on further. So due to the complex nature of soil and their behavior, a hybrid approach to foundation design is adopted. Most of the codes in which bearing pressures are checked, it is based on working stress method, and the foundation members are designed using limit state method. So why I am calling it as hybrid method, I am calling the design of footing as hybrid method, because now we have to deal with both soil design as well as structural design. So what the code says, design our footing in such a manner that you are checking the bearing pressure of the soil by working stress method, and after checking the bearing pressure, design the foundation by using the limit state method. So what are all this, I will be making more clearer to you. Let's move on to the next point. Both ultimate limit method and the serviceability limit checks are to be satisfied. So since our the point number 1, it says hybrid method, we should use both working stress method and limit state method. Working stress method is for the bearing pressure, and for designing the footing we should use limit state method. So both of the method should be satisfied. Now moving on further, plan area of footing is selected to limit the maximum soil pressure induced below the footing within the allowable soil pressure, known as the safe bearing capacity of soil and represented by it. So now we will be talking about in what manner the footing should be designed, that both working stress method and the limit state method should be satisfied. So in a footing, what we have how many, like designing a footing, what does that mean? That mean, firstly we should have a cross section of footing, that is L and B. Secondly, we should have some depth of this footing, that is D. And thirdly, we should have some reinforcement in this footing. So these three criteria would entirely be able to design the footing. So now IS code says to, what does it says, to design, to decide or to finalize the cross section of the footing, that is L and B, we should use working stress method. Why we should use working stress method? Because the cross section of the footing, it is based upon the bearing capacity of soil, and the safe bearing capacity of the soil, it is evaluated using the working stress method. So that is the reason we should evaluate the length and the breadth, that is the cross section of my footing, by using working stress method. While the second method in which we are supposed to now evaluate or find the depth of the footing, in that case, since the depth of the footing, it is based upon bending criteria. I will be explaining this you more in detail. Since this the second step, which is evaluating the depth of footing, it is based upon the bending criteria, we are supposed to use limit state method. And the third step in which we are supposed to evaluate the reinforcement should be evaluated by using, again, limit state method, by using the bending criteria. So this is the manner in which we should design the footing, by using both working stress method and the limit state method. Let's move on further. The safe bearing capacity is determined using principle of soil mechanics, and includes the safety factor for service loads. Okay, so this I already told you. The safe bearing capacity, it is evaluated based upon service load conditions. Service load conditions means whatever load it is acting on the structure, that load we are using it directly without any partial factor of safety, or what I should say better is, I will be using a factor of safety of 1. Now what does the last point says? Partial load factors are applicable to serviceability limit state, should be used for calculation of footing area, that I have explained you. Now let's move on further. So the safe bearing capacity may be expressed in terms of gross or net pressure at the foundation level. So suppose if I have a foundation, so the safe bearing capacity, it can be expressed either in the form of gross pressure, or it can be expressed in the form of net pressure. So gross pressure is nothing but we have to consider the P plus delta P. Delta P is what? The P is nothing but the load coming from the column. Delta P is the, it constitutes of self weight of that footing plus the surcharge load which would be coming on this footing. So gross pressure is the entire pressure coming on the footing, and net pressure is only P. So that is only the load which is coming onto the column. So this is what this slide is trying us to say. So just remember, the net pressure on the footing, it can be either, sorry, the pressure on the footing, it can be either gross pressure or it can be net pressure. Gross pressure will constitute of surcharge load, load coming from the column and the self weight, while the net pressure will only consider the load which is coming on the column. So just remember these 2 points, what all the pressures which can come on the foundation, and the other points where how we will be designing the footing based upon the pressure, safe bearing capacity of soil. I will decide length and the breadth of the footing. Then the depth of the footing, it will be decided based upon what? It will be decided based upon the limit state method, and finally the reinforcement will be judged by the bending criteria. So here I have made it more simple for you. I have like made a hierarchy of this design procedure. So design of footing, it is mainly considering designing the cross section, that is designing the L and B. So this is the L and B. Now how I should design this L and B? It should be designed based upon the safe bearing capacity of soil. So since safe bearing capacity of soil, it is evaluated based upon working stress method. So that is the reason I will be using working stress method for evaluating length and breadth. Now the second design of footing, the second means the other dimensions which I need to design is L and B are over. Now I need to design D. So depth can be evaluated based upon shear criteria. So this footing, it is critical in shear rather than bending. So based upon the shear criteria, I would be designing this depth of the footing. So L and B, it will be designed based upon the safe bearing capacity, while D, it would be designed based upon the shear criteria, and the reinforcement, it would be designed based upon the bending criteria. So two types of shear can act upon the footing. Those are one-way shear and the two-way shear. It can be also called as punching shear. So now just answer me one question. Uh, I told you the L by B of this footing, I will design it based upon the working stress method. So you already know that for limit state method or for the ultimate state method, what we do, we adopt a factor of safety of 1.5, partial factor of safety of 1.5 to the load. Okay, so to the load we take this factor of safety, while in working stress method what we do, the load, we do not take any partial factor of safety. Like the partial factor of safety is 1, we directly take P. And I told you the we will be evaluating the length and the breadth based upon the bearing capacity Q. So Q, you know, it is divided by, it is a pressure, so force divided by area. And so just answer me this question, uh, whether the area evaluated using working stress method will be more, or by using limit state method it will be more. By using which method will the area of footing will be more, by working stress method or by limit state method? No idea. It's a simple question. Akhilesh, you are not audible. There is some problem with your microphone, I think. You are not audible at all. You can type your answer in the chat box if you wish to. Just type your answer. Are you typing? In LSM method, the area would be more. Yeah, it is obviously because we are using a factor of safety of 1.5 here. Okay. So in LSM and in working stress method. Okay, fine. Now let's move on to safe. Okay, L and B we can easily evaluate it. The length and the breadth of this footing we can evaluate it easily. Now let's evaluate the one-way shear and the two. Let's learn to evaluate the one-way shear and the two-way shear. So since it is the shear, we should be firstly knowing what are the critical sections. So according to IS code for one-way shear, the critical section is D. It is at a distance of D from the face of the column, whereas in a two-way shear, the critical section it is at a distance of D by 2 from the face of the column. So since one-way shear, it can act either on one of the side of this column. It can be either on this side. Let me change the color of my pen. So it can act either on this side or it can act either on this side, and that is the reason we are only supposed to take the critical one. While in two-way shear, the entire area which is at a distance of d by 2 from the face of the column has to be taken, because punching shear it's something, it is something which occurs because of punching of this column from all of the four sides. So this is the punching shear. And how to calculate the one way shear? So just simply multiply the area of the shaded portion with the gross or the net bearing capacity of soil, and here also just multiply QU with the net bearing capacity. So how does this formula comes? It simply comes by this area. So B by 2, what would it be? B by 2 minus C1 by 2 minus D. So if you solve this, you will be able to get this. And here also, how will you get this formula? Just multiply by the area of the shaded portion, critical section, critical area for two-way shear. So what it will be? Total area is what? Sorry, QU into what is total area? Total area is B into B, that is B square. So I will just uh, subtract it from the area of this bigger square. So what it will be? It will be C1 plus D by 2 square. So this is the way I got it. So now you know how to evaluate the one way shear and the two way shear acting on the footing. Then you need to design it accordingly. Now one way shear, this was the this is the method to find the one way shear forces. So one way shear forces you can find it from here. But now how to evaluate the shear resistance? So in case of one way shear, the shear resistance you can evaluate it by using our normal method, that is the method which we use in beam. How we used to evaluate the shear resistance in beam was based upon the longitudinal reinforcement in that beam. So based upon that longitudinal reinforcement and the grade of concrete, we can get the shear resistance of that beam. So in the similar fashion, you can evaluate this one way shear of footing also. But how to evaluate the shear resistance of two way shear? Because by using these formulas, we will get the shear force which is acting on the footing. Now based upon this shear force, how to like judge the footing, how to decide whether the footing is safe or not? So for that purpose, we are talking about shear resistance. So for one way shear, you can find the shear resistance based upon the method which we used in beam, that is based upon the longitudinal reinforcement. We have to see it from the IS code, the percentage of longitude and the grade of concrete. And two-way shear, there is some criteria which is mentioned in IS code. So the two-way shear, or the allowable shear in two-way, it can be calculated by using Ks into tau s. So what is Ks? Ks is nothing but zero point 0.5 plus beta s, beta c. So this is Ks, and the allowable shear stress is nothing but Ks into tau s, tau c. toss is nothing but for limit state method which we are using, it is 0.25 root fck. Now ks is zero point 0.5 plus beta c, so this value it should not exceed 1, so this is always equal to 1 or less than 1. So beta c is what? Beta c is the ratio of the length and breadth of your footing. So that's what all I need to show you, how to calculate the resistance of the footing in two-way shear. So now you have the forces as well as the resisting capacities. So based upon that, you can design the footing. And the last but not the least is the critical section for bending. So here you can see the critical section for bending is at the face of the column. So it is quite obvious. This footing, if you look at this section, this will behave as a cantilever. So it will bend like this. Like if you look it from the side view, then this will behave like a cantilever. It will bend like this. So the critical section would be here. That is the moment will be maximum at this point. That is WL square by 2. If W is the total weight acting on it. So in this manner you can find the bending moment, and based upon this bending moment you have to calculate the longitudinal reinforcement in this footing. Okay, so how did you arrive to this formula now? Mu, so the safe bearing capacity of soil is Qu. So Qu, it has a unit of Newton per meter square. So if you consider this as the UDL, then just multiply it with the width which is perpendicular to this UDL. So I will multiply it with B, and after I multiply it with B, I will, this is the UDL actually. What is this? This is UDL. And now based upon this UDL value, you have to calculate the maximum moment at this critical section. So moment will be what? Qu into B, and WL square by L. What L is what? B by 2 minus C1 by 2. So this is L square by 2. So QB, if I bring this out from the square, it will be 8. So this is the way I get this formula. So now I have summarized all of these three criterias which will be used for finding the depth of my footing. So the depth of the footing can be found by one-way shear criteria or the two-way shear criteria, because my footing, it is critical in shear and it is not critical in bending, but for bending we would be providing again the shear not shear reinforcement, the the flexural reinforcement, and those flexural reinforcement would be based upon this formula. How this formula is came, we have derived all of them one by one. Okay, now let's move on to one of the problem. So design an isolated footing for a square column 450 by 450 mm carrying a service load of 2300 kilonewton. Assume soil with safe bearing capacity of 300 kilonewton per meter square, which is at a depth of 1.5 meter. Assume M20 grade of concrete and Fe415 grade steel. Also assume a cover of 75 mm. Okay, so the cover of the footing, it is given as 75, and they have given us the unit weight of soil which is 18 kilonewton per meter square. Use 16 mm longitudinal bars for footing. Okay, so this 16 bar we would be providing it for flexural reinforcement in the footing. Okay, so how do we initiate? Come on, how do we start? What it is given? It is given. I have a what I have a column. Okay, so I have a column of 450 by 450, and above that column I have a load of P which is equal to 2300 kilonewton. This column has a planned as a cross section of 450 by 450, and this is the column with footing. I have to design this footing. So just try to make sense of these questions like I am doing. So what they are saying me, the safe bearing, that is the SBC, or what you call it as Q, it is 300 kilonewton per meter square for the soil. Safe bearing capacity they have already given me, but we know based upon the load which is acting on the column what would be the, and please note down this term which is given in the bracket, gross. So they want us to take the QU as the gross pressure of the soil. What does gross pressure means? Come on. Gross and net. Gross pressure means,
The taking surcharge also.
yeah. Now I think you have repaired your microphone. Okay. So gross means you have to take surcharge as well as the self weight. So you we know what the pressure which would be coming from the soil, it would be equal to P plus delta P divided by area. Area, do we have area? No, we don't have area, because that is the design which I have to do by finding L into B of this footing. Now since the column which is uh, attached to this footing, it is a square column, I would be preferring to design a footing which is also a square. Okay, so now my it will reduce down to B square or L square, whatever you want to take it, because it is a square. Now I have P. What is P? P is 2300 kilonewton. Do I have delta P? Delta P will consider what all loads? It will consider the self weight. How can I have a self weight? I don't even know what is the depth of this foundation. What is the L by B of this foundation? How can I have the self weight? So let's see how will we have it. The second is, along with the self weight, I would be also having surcharge load. So now you already know what you know. You know that we would be designing the cross section of this footing based upon working stress method, because the safe bearing pressure is evaluated based upon working stress method. So now this P, the factored load would be P itself. We won't be multiplying it with 1.5, because multiplying it with 1.5 is something which we do in limit state method. Here I have to take one only, but I don't have delta P, so I will have to assume some delta P. Based upon that delta P, I will find the cross section of this footing, and afterwards we would be also checking whether the assumed delta P is correct or not. Also, one more information it is given in this question. My footing, it is lying at a distance of 150 mm. Okay, so bearing capacity of 300 kilonewton per meter square at a depth. So the bearing capacity of soil, it is at a depth of 1.5 meter. That means my footing is resting at a depth of 1.5 meter. Okay, now I have one more quick question for you. Since it is Q is what? Q is what? Where is Q? Q is 300 kilonewton per meter square at a depth of 1.5 meter. Now, can you guess what will be the value of Q at a depth of 1 meter? Anyone? I don't want a value. Just tell me whether it will be less than 300 or more than 300. This is an aptitude question. Logically answer me.
Sir, it will less.
Yes, it will be less. Why?
So because as a depth less, so weight of the soil also means surcharge, and surcharge is less,
Yes,
and
yes. Okay. Okay, I
no.
understood. Let me now like clarify more. When we go for the when what we do when we go for the construction of foundations, what we do, we just dig the soil. We go on digging the soil, we go at greater depths unless we get higher bearing capacity of soil. So the greater the digging we do, or the greater at a higher depth we go inside the earth, the higher would be the more compact would be the soil at a greater depth. So the more depth we are at a more depth we are constructing the footing, the more would be the bearing capacity of soil. So that is the reason we prefer to go it as deep as possible, because the more deep we go, the more will be the bearing capacity of soil. So this is like, you can interpret it. This was like just for making some sense of these questions. Okay, so now I think we are ready to solve this question. what all you have here, you can just read it from the question again if you wish to. So let's start. Firstly, I will be starting my designing by evaluating L into B. For evaluating L into B, I need P plus delta P. I don't have delta P, so let's see what I will do. So determine footing size. So I am assuming footing and backfill weight of zero point 0.1 P. So I am assuming delta P to be equal to zero point 0.1 P. This is my assumption. So this is the way usually we start the design of any structural component with an assumption. Based upon that assumption we reach to a final design, and based upon that design we recheck our assumption whether my assumption which I took is correct or not, whether under that assumed values of my load, whether my footing is coming out to be safe or not. If it is not coming out to be safe, I will again redesign my section. So this is an iterative process. So based upon that, the base footing area I am taking it as 1.1. How this 1.1 came? P plus zero point 0.1 will give me 1.1. So QA is what? P by A. Area I can find it. A will be equal to 1.1 P by QA. So from here I got the area of cross section. Since I wish to have a footing which is of square plan, because the column which is coming onto this footing is a square, so it is better to have a square footing also. So I will just simply take the root of this, and I am getting a size or the side of the square footing as 2.9 meter, and I am rounding it off to 3 meter by 3 meter. So this was all about the evaluating the length and the breadth of this footing. Now the other thing which I have to do is I have to find the depth of this footing. So this is like we are doing the design of this footing step by step. So come on, answer me. How to evaluate the depth? What are the design criterias for depth? What are the design criterias for depth? One way shear and two way shear. So let's first check it for one way shear. So now again please remember, I already told you to evaluate the size of footing I'm using working stress method. That's why I am using the service load, that is I am not multiplying it with any load factor. While when I determine the D, that is the depth of footing, I will be using ultimate limit load method, limit stress method. And this limit stress method, it has a partial factor of safety of 1.5 for load, and that is the reason I took this 1.5. And while designing the depth of footing, I am not taking the surcharge load. That is to be on more not economic, but to be on more safer side, because the it will reduce the depth. The surcharge load will reduce the depth. So I am taking only the load which is coming onto the column. Okay. So based upon that, I have a QU value. Area I already have it 3 into 3. So I got net soil pressure at ultimate load. So I'm to be on conservative side, I'm not including delta P. And now I will be doing what? I got the net pressure. Now I will go for one way shear. So one way shear would be formula. I have already told you. What is this formula? This formula would give me what is the one way shear acting on my column based upon this net pressure. This net pressure I evaluated based upon the load coming from the column. So everything is related. Now, okay. Okay, so from this formula, what I will get? From this formula, I will get the shear force. Now, this shear force is like the load which is acting on the footing. I need to find what? I need to find the shear resistance. I already told you the shear resistance for one way shear. We calculate it based upon the design criteria which we used it for beams. So, how did we find the shear resistance in beams? VUS. Come on. How did we find it? Allowable shear resistance of beam. Any one of you from
VUS minus tau CBD.
VUS minus tau C BD. Okay. Okay, so what you are saying me is this. So how to calculate TOSI? So basically, okay,
From percentage ASC, sir.
yeah, exactly. So basically, let me clarify more. Since this is the beam, in beam we had longitudinal reinforcement, that is the flexural reinforcement, and stirrups. So now in footings we would not be providing any stirrups. So that was the reason what we did. The shear force which was acting on the beam, it was VUS minus TOSI BD, because TOSI BD was what? TOSI BD was the additional shear, what it was, additional shear resistance which was provided by the concrete. But in footing we won't be providing any stirrups, so whatever would be the shear resistance, it will be provided by the concrete itself. So what would be the shear resistance in case of footing? It will be TOSI into BD. How we get TOSI? It is based upon the longitudinal reinforcement, percentage of longitudinal reinforcement, and the grade of concrete, M25 or something like that. But in footing, do we have we up to this point have we were we able to provide the longitudinal reinforcement? At any point, did we provide any longitudinal reinforcement in our footing? We don't know what are the longitudinal reinforcement, but we know the grade of concrete. We know what grade of concrete we will be using. So again, to find the shear resistance, what we will be doing, we will be assuming a percentage of steel. So in this case, we are assuming 0.25 percentage of steel. Don't worry, this assumed value of longitudinal reinforcement, we will be cross verifying it afterwards, whether the assumed value is coming out to be safe or not. So for the time being, just remember we are assuming the longitudinal reinforcement. We have grade of concrete, and now we will be finding TOSI. TOSI is coming out to be 0.36. So whatever would be the shear resistance in case of footing, that shear resistance would be based upon the shear resistance provided by concrete only. So this is the shear resistance, and this shear resistance, for our footing to be safe, this shear resistance, it should be coming out to be greater than the shear force which is acting on it. I hope you are able to understand. There is nothing like me to explain more on this. The shear resistance, it should be more than the shear force. So now let's see. Okay, this is what I have already shown you. So based upon this inequality, I have substituted VC1 as TOSI into BD and VU1 as this value. This is from the formula which we have derived based upon the critical section of footing. And now everything is known in this inequality equation. The only thing which is unknown is D. So I will get D. I'm getting D has to be greater than 658 mm based upon one-way shear criteria. Now another criteria for the depth is two-way shear criteria. So in two-way shear, what we have is, in two-way shear what we have this shear force which is acting at the critical sections. This formula also we have derived. It is acting at a critical section, it at a distance of d by 2 from the face of column. Now what is the shear resistance? Come on, in two-way shear what is the shear resistance? Yeah, I have already told you, in two-way shear the shear resistance is given by kc TOSI into ks. What is ks? Ks is point 0 point sorry zero point 0.5 plus beta. What is beta? Beta is the ratio of sides of my footing. Okay, so what is beta in our case here? What is beta for this case? Beta is what? My footing is of size 3 meter by 3 meter. So what will be beta? Beta will be 1, 3 by 3. But I know zero point 0.5 plus beta, it should not be greater than 1, because 1 plus zero point 0.5 would be 1.5. So I'm restricting it to 1. Now I will find the shear resistance in two-way shear. So this shear resistance, it will be coming out to be 0.25 fck, root of fck, and beta I'm restricted into 1. Now I will again use that inequality. the shear resistance, it should be greater than the shear force in case of two-way shear also. So here I'm getting D as 625. So in one-way shear I'm getting D as this, in the two-way shear I'm getting D as this. So greater of these two would be used. So I'm using it as 658. Now 658 is the effective depth cover. It is given. The questions asks us to use a bar diameter of 16. So after adding it, I will get an overall depth of 750. So this was all about the L by finding the cross section of footing and the depth of footing. Now let's move on further. So I have averaged it, I have rounded it off to 750. So again I'm finding D. So that is you can do. Now now see, now please try to understand this. This is like we have reached to the end of this problem, but now some important checks are to be given because we have assumed many things while designing this footing. So we have this footing like this is my column and this is my footing. So if this is D is what, 750 mm. And what was this height given? Can any one of you tell me? The depth of the footing was how much below the ground level? How much it was? The searcher. Yes.
It is 1.5.
Yes. So this was 1.5 meter, and the depth of footing which I get is 750 mm, which is 0.75 meter. So what would be the remaining depth of this soil? It would be 7.5 meter, 0.75 meter. So see, now based upon the dimensions of this footing what I have designed, I can find the surcharge load 0.75 meter. So now I will find what is the surcharge load. Surcharge load plus I can also find the self weight, and that I can add with the total P by A. So this would be the total pressure, and now this total pressure I will equate it with what, with 1.1 P by A. So this 1.1 P by A which I assumed it in the previous slide, this 1 point, this it should come less than this Q value. This Q should be greater. No, this should be greater. What I have assumed, it should be greater, so that if I assume higher load are acting on my footing and I have designed for that higher load, then it is fine. But if the actual load it is acting, it comes out to be higher, then I will have to redesign. I hope you are able to understand. So I'm finding the actual pressure and I will compare this actual pressure based upon what I have assumed. Okay, so this actual pressure it is coming out to be 288, but what QA did I assume? Let's when go on to the previous slide and see. Okay, I have not. Okay, so this is no, not this, not this. This is 1.1. I have not calculated it. You just calculate it and find a value. You will notice that it is coming out to be more than what actually it is acting onto the soil. Okay, so now since what load I have assumed it is less than what is actually, what load I have assumed it is more than what actually it is acting on the footing. Because of that, whatever I have designed is okay. If whatever I have assumed was less than what it is acting actually on that column, on that footing, then I will have to redesign it. If you are not able to understand, please look at this video once again. This is not very difficult, I think. So now finally I have designed L by B, I have designed D. Now finally what remains is the reinforcement, which will be designing based upon the moment formula. Also we have like uh, calculated based upon the critical section. So based upon this moment and what you have learned in beam, you can find the reinforcement. So R is mu by bd square. From R you can evaluate the percentage of reinforcement. So percentage of reinforcement, it is coming out to be 0.27. So now 0.207% it is the actual steel which is provided, and what we have assumed is 0.25 percentage of steel. So if you look at the shear criteria, in the shear criteria we have assumed a higher percentage of steel. So for assuming that higher percentage of steel, I am getting a greater depth of my concrete. So again, that is like fine for me. So now I am, since I have assumed, see, just I want a quick answers from you. uh, in case of beam, if I have a beam and I have some longitudinal reinforcement, so because of that longitudinal reinforcement, my shear capacity of this beam, it increases or decreases?
Decreases.
Oh, does it decreases or it increases? Because of this percentage, the higher the percentage of steel in my beam, see, we are finding the TOSI. TOSI is what? It is the additional shear reinforcement which is provided because of concrete plus because of longitudinal reinforcement. So the higher the grade of concrete, the higher will be the shear resistance, and the more the shear reinforcement which is provided, the more will be the shear resistance. Okay, because this longitudinal reinforcement, the higher the longitudinal reinforcement, the more it will be able to resist the cracks which are developed due to the shear. So now, previously what I did, I assumed 0.25 percentage of steel, and I evaluated some TOSI value, and based upon that TOSI value I have evaluated D. But what actual percentage of steel it is coming is 0.207. So now, like, it would be very painful for me to again go back and take a value of 0.207 and a grade of concrete and again find the depth. So a smarter way is, since the percentage of steel it is coming out to be 0.207, I can provide any percentage of steel which is greater than this value. I cannot provide less than this because less than this will lead to failure, but greater than this I can provide. So I am like, what percentage of steel I have assumed previously, I am providing that percentage of steel. Okay, I hope you are able to get this. And I know this would be uneconomical, so if you wish to, you can again go back and design based upon this percentage of steel, you can again design. But a smarter way to deal with this problem would be, just for the problem sake, you can just replace it with whatever percentage you have assumed. But whatever percentage of steel, suppose if you would have assumed a percentage of steel which was 0.15%, then there would be no option. Then you would have to do again redesign thing. But since you have assumed higher percentage, then that was fine. So now I am considering 0.25 percentage, and based upon this 0.25 percentage I am calculating the percentage of steel. And in question they have given, you have to assume a bar of 16 diameter. So here, yeah, you have to also give the check for the minimum percentage of steel. And this minimum percentage of steel, we have looked at this formula in slabs. So footing is a kind of slab, you can see. So based upon this 16 mm5, I am finding the spacing, and this is the final sketch of my footing. So this was all about this problem, and there are many terms and many checks which you have to do at the end because of many assumptions which we use before beginning the design of this footing. So that was all I had planned to take in this class, the design of footing. If you have any doubt, the floor is open for you.
Sir, it's my query is related to the columns.
Yeah.
Uh, Sir, according to the IS